wanted a little bit more agency about how I shaped my life, whether it's geographically or sort of the pace of things. If you've had people on from the academic life, you know that sometimes those choices aren't always up to them. That plus, like I said earlier, the desire to make a little bit of a change in not just the specifics of the research I was doing, but sort of the practical nature and the direct contribution to society, all that sort of converged to have me make that particular choice.
Hello, everyone. Welcome back to the It's a Material World podcast. I'm Puneet. I have David joining me today for this podcast episode. How's it going, David?
Pretty good. Not too much, just going through school, about to hit midterm season. So very exciting stuff. Do you miss exams?
I do not miss exams. My girlfriend was talking about how she has an exam as well because she's in an online master's program. And I was like, this is one thing I definitely do not miss. Good luck with that. But yeah, I know we were talking offline and we were kind of astounded. You're closing in on 6 years of battery research. How does that feel?
Yeah, that's wild. No, it's definitely been a journey. It feels like almost a PhD, but not really. So it's been quite a time, but I feel like I've learned a lot from my 6 years in battery industry, and hopefully through this podcast, which happens to be on lithium-ion batteries and electric vehicles, I can showcase some of that. And I think that some of the things that resonate with me were the first being that hands-on experience is the best way to learn. And so I never formally took any battery classes, and yet I would still think I know a fair amount. And I talk with Jeff in this episode about some of the more intricate parts of a battery that's beyond the baseline. But the second one is just talking with him about the next steps of batteries. And so one of my favorite sayings from an old CEO that I interned at his company was, there's only been like 6 or 7 main innovations in batteries. If you think about that, the battery is almost one of the most important things we've ever done, and there's only been 7 iterations. That's not that many. And so when we look at these new innovations, you could be the 8th. And so it gives a lot of like emphasis on let's go find the next big thing. And it has, what I think has kept me in the battery industry for so long is just, even though that it's very important, it's still kind of new. We're figuring out a lot of things, and there's so many different avenues to improve it that there's just so much to do, and you can kind of pick what interests you.
Yeah, that's what astounded me about just the complexity of the battery ecosystem, which Jeff mentioned. There's just so much research you can do, as you mentioned, like anode, cathode, electrolyte, and everything in between, literally, right? And so kind of my favorite part of the podcast episode was just how we talk through kind of what are the 3 maybe constraints or just reasons why EVs aren't more adopted in today's world. And it boils down to cost, range anxiety, and charge, right? And something that was super powerful was that he mentioned that material science can and will solve all of these challenges, which makes it just so much more exciting to be in this field, specifically in battery research. So yeah, I don't know. That was my favorite part of the episode. Do you have anything else that our listeners should look forward to?
Yeah, I think that we briefly talk about it, but the idea of taking something that works in the lab and scaling it to in every single car is just a complete feat of engineering. And so just throughout the entire life cycle, material scientists play such an important role because it takes material science to make it work theoretically, to make it work in lab, and then make it work at all scales. And so I just think there's parts to be played by material scientists throughout the entire manufacturing line, from R&D to a car, and then also from the research with each part of the battery cell. So just kind of re-emphasizing how flexible and diverse a field can be within just one little cell.
Yeah, and it seems like material scientists will continue to be in high demand in the space, which is, it's very energizing. So before we get into the episode, just heads up, we have a Discord MSE community, and we have events in there. We ask questions, and it's just a great place to kind of interact with other people who are on a similar journey as you. So you can find that link to join in the description. So yeah, without further ado, let's get into the episode.
Meta Material Inc. is a developer of high-performance functional materials and nanocomposites. Meta delivers previously unachievable performance across a range of applications by inventing, designing, developing, and manufacturing sustainable, highly functional materials. Meta is a fast-growing company with a positive and committed work culture and a phenomenally talented workforce. Our employees are inspired to do exceptional and innovative work and are proud to contribute to the success of the company, and they are our greatest asset. Meta attracts people from all countries and cultures with over 35 spoken languages represented across all our teams. Meta believes that diversity drives creativity and innovation. With locations in Canada, the United States, the UK, and Greece, Meta is growing and is looking for new talented people to join the team. If you're passionate about doing your best work, making a difference, and having fun while doing it, apply to one of our open positions at metamaterial.com/careers. All right, hello everyone. For today's episode, we're very excited to welcome Dr. Jeffrey Cain, Senior Researcher at General Motors Research and Development. As a Senior Researcher at General Motors R&D, Jeffrey focuses on emerging materials, chemistries, and nano and microstructures for next-generation lithium-ion battery technologies. Thank you so much for joining us today, Jeffrey.
Great to be here. Thanks for having me.
Yeah, I think this will be one of David's favorite episodes. And I did some solid state electrolyte research way back when, freshman, sophomore year. So maybe I can contribute a little bit. But just to start out, we just wanted to hear your motivation for getting involved in battery research, and specifically with respect to EVs, electric vehicles.
Yeah, that's a really excellent question. Getting into battery research was actually something of a pivot for me. My PhD and my postdoc had been on more fundamental nanoscience, a lot on basic properties and synthesis of things like nanotubes and graphene analogs. And as I was finishing my postdoc, I just sort of personally wanted to change a little bit. No one spends their entire career working on one thing, and I felt like it was a nice natural turning point to try something new. And I chose to move toward lithium-ion battery research because I was really wanting to contribute scientifically to something that is a really pressing problem in the world. There are a lot of ways for material scientists to get involved in industry, and that's the transition I was making from sort of academia to industry. And I specifically chose to get involved in the automotive industry and EVs because I thought it was the best way to use my skill set to, like I said, contribute to solving this massive problem, specifically of global warming and climate change, that I could bring to the table. It also was just interesting to me. It's a really fascinating area of research. I think we'll talk about what goes into a lithium-ion cell, and it's this really complex ecosystem with a ton of material science, all the way from like the fundamentals of electrochemistry to the consumer aspect. And so it sort of scratched all the itches, as it were, and turned out to be just the right research area for me at the time. And I'm still enjoying it.
That's nice. I was just wondering, did you know, even when you were getting your PhD, did you know that you would end up in industry, or how did you end up making that decision between continuing like postdoc, et cetera, versus the industry?
That is an interesting question, and one that I think starts to edge into the more personal reasons people make choices. After I finished my PhD, I chose to do a postdoc. It was a joint postdoc in an academic and national lab setting. It was at UC Berkeley and Berkeley Lab. And I chose that setting because it sort of kept all of my options open. I was still sort of had a foot in the academic path, a foot in the national lab path, but the industry path I knew would also always be there because material scientists are so heavily in demand. And so I made that choice because I still didn't quite know which of those paths I wanted to take. And like I said, your question sort of touches on some of the more personal aspects. And I ended up choosing industry because I wanted a little bit more agency about how I shaped my life, whether it's geographically or sort of the pace of things. If you've had people on from the academic life, you know that sometimes those choices aren't always up to them. That plus, like I said earlier, the desire to make a little bit of a change in not just the type of research, not just the specifics of the research I was doing, but sort of the practical nature and the direct contribution to society, all that sort of converged to have me make that particular choice.
Awesome. And so when we think about going into a career in battery research, something that's a little different is that there's not really like a battery major. And so it takes from a lot of different places. And so how did you demonstrate your values in interviews, despite batteries not being a huge part of your previous research and only being the latest thing you did?
Yeah, that's a really great question. It's one I've gotten before, and I think people need to give themselves more credit when it comes to going into interviews like this or finding a job. We spend so much time in undergraduate even, but graduate school and postdoc, deep diving on single problems, and you start to think that that becomes your identity. But I had to sort of remind myself, and in the process of these interviews, remind others that I'm a material scientist first, and I was studying a specific type of material for those 10 years or whatever it was. But really, I just had I had to show that I was comfortable sort of traversing that process, structure, property, performance paradigm that MSCs all know. And while I had applied that to a certain material family before, I could apply it to a different one in the same way. And I had all the skills to do that. And in some ways, that's a little bit soft when you're in the interview talking about the conclusions that you drew and how you drew them, the techniques that you use. And some, it's a little bit more quantitative, showing, oh, I worked with electron microscopy, or I worked with this technique or that technique. For me in particular, it was some aspects of, like I just noted, electron microscopy, some specific characterization methods. But in the interview, really just showing that I could take a problem and solve it or make a contribution in a meaningful manner in a way that made sense within that paradigm that I described. So it's more about showing your general expertise than it is about specific knowledge. People who did study batteries in their postdoc and PhD are perhaps at an advantage when it comes to looking for jobs in industry, because not only do they have the general knowledge, it's definitely not out of the realm of possibility for people to switch fields like I did. And in fact, a number of people that I finished grad school with or postdocs with at some point in their career in the last few years have pivoted, and it's worked out very nicely for them as well.
Yeah, I like that story because I think, just like you mentioned, especially in this field of material science, it's not necessarily like super rare for someone to be able to pivot and transition to completely different industries. I was able to do that. I had an internship in an aerospace company, and then like a polymers internship, and was able to switch all the way to medical devices. So I just like the fact that you touched on kind of the problem solving aspect. And I just wanted to hear, David and I, we both are finishing up or have finished up kind of like our master's program. We did a 5-year BS MS, but I wanted to get your input from the PhD and postdoc side of things, of kind of what additional value does that provide when you're kind of entering into the job market?
You're asking, what does a PhD or postdoc, how does that add value?
Yeah.
Generally, I think it depends. It sort of decides sort of the track you'll be on, maybe within a specific company. For instance, having a PhD, having postdoc experience, I am on very much a research, technical track within my company. And that's the one I chose. That's why I got a PhD. That's why I did a postdoc, because I enjoy lab work, and I also enjoy sort of managing more research-based projects. And whereas someone with a master's or a BS might take more of an engineering track, or even an engineering management track. And so ultimately, your training sort of dictates which of those paths that you end up on. And this is just the one that I happen to enjoy the most. And so that's why I've chosen it.
Awesome. So yeah, I guess we can go into kind of the focus of today's episode, which is batteries in EV applications. And so just generally, I would love to hear from you kind of what materials are currently used, and can you maybe talk through, you mentioned that paradigm, structure, property, performance, processing, relationships. Can you talk through the properties that make them suitable for this application? Yeah.
Like I mentioned earlier, batteries are a really sort of complex ecosystem made up of all these different materials and all these different types of materials. I'm sure your listeners, and I know for a fact that you guys are familiar with the components that make up a cell, but you have an anode and a cathode. You have an electrolyte, which acts as a medium for lithium ions to shuttle between the two. You have a separator sandwiched in between to electrically isolate the two electrodes, but allow for that shuttle of ions. And then on either side, you have current collectors. For the cathode side, usually it's aluminum, and for the anode side, usually it's copper. And if you look at each of those components, they're all made up of different classes of materials. The current collectors are metals. Separators are polymers. Cathodes are generally these more complex transition metal oxide materials. Electrolytes tend to be carbonate solvents with lithium salts. And anodes generally are graphite or graphite containing materials, carbonaceous materials. And so there's a huge spectrum of materials that go into a cell, and thus a huge sort of spectrum of expertise that it takes to engineer each of those aspects. And I should really highlight that each of those aspects, each of those components really are currently undergoing a ton of optimization, a ton of research. There's no aspect of the cell which people deem solved. And so there is a great deal of research across each of these types of materials that is available. But going back to your original question, I think a good example is to take the anode as sort of a really nice instance of what you're describing, this structure property or process structure property performance paradigm. The current anode of choice is usually graphite, and there are little twists on that different manufacturers have made, but generally it's graphite. And what makes graphite so wonderful and perfect for this particular application is its crystal structure. I'm sure all of you know that it's composed of these layers of hexagonally bonded carbon. You can sort of think of it as chicken wire stacked on top of each other, and they're strongly bound in plane, but out of plane between the layers, it's just weak van der Waals forces that make these perfect lithiation pathways, these points of egress to get into the material and hold on to the lithium. And because of that very unique crystal structure, we can pass lithium in and out over and over and over again. Graphite cycles incredibly well and is very durable, which is one of the main performance metrics that people really require out of a cell. And like I said, that is all derived from how those carbons are bonded in that material. Carbon takes on a lot of different coordinations and a lot of different structures, but because of that layered structure, we're able to get exactly the type of performance out of it that we desire. And like I said, I think that's perhaps the best example and most easily accessible example of how the atomic scale of a material impacts performance at a very tangible level.
And yeah, I think that you did a great overview of the battery. I think that's a very good base level, but going up a step without going too deep, there's a few intricacies that have really interesting material relationships. And so could you please go into, there's a few of these, so I'll just do a little bit of a rapid fire here. So the first one that I think would be interesting to talk about is the SEI. Could you explain what that is in a little bit? And in fact, it's actually what makes the lithium ion such a powerful tool. So could you explain that reaction?
Yeah, so the SEI, the solid electrolyte interface, is the layer that develops upon cycling on there's the SEI on the anode side, but you also have an analogous thing on the cathode side. But it's a layer that develops upon formation and upon cycling that sort of holds it all together. And I don't want to dip too far into the next perhaps the next question, but it's a really critical component of the cell when it comes to next generation materials, things like silicon or lithium metal. I'm not sure what exactly you mean by, or what you're sort of getting at, what you'd like me to explore beyond what the SEI actually is. But
no, that's great, because a lot of these battery terms, a lot of people know like the basic cathode and anode, but some of the things that make a lithium ion work, like the SEI, it's the basis of it is just, it makes it very stable and allows for lithium ion coulombic efficiency, or how many lithium ions you get in and out, very stable. And so it's like a very important part that I feel like a lot of people overlook. The next thing that I would love for you to talk about very briefly is, why do we use an aluminum current collector on the cathode and a copper one on an anode? I know that it's just kind of given, but why is that?
Yeah, it has to do with the potentials in the cell and how the different metals respond to those potentials.
Mhm.
And because of the potential that the anode is at, and vice versa, the cathode, the aluminum and the copper hold up essentially to those potentials. We don't get any copper dissolution. We don't get any aluminum dissolution. So they're just very stable during operation
Mhm.
and fill those needs very specifically for the anode side and the cathode side. You couldn't, for instance, switch those because life would start to get messy. But yeah, they're essentially just very stable under the operating conditions within a cell. We don't lose. We're not we're not getting any aluminum or copper dissolution into the electrolyte.
No, that's great. And so I think I just wanted to ask those two questions because I feel like we may know about them, but don't know the real reasons why. And it just is the next evolution. And then the SEI is things that people have spent years studying. And so each of these topics that we're talking about go even further.
Yeah. Oh, the SEI very in particular is really critical. Like I said, with next generation materials, it acts as sort of a buffer for the morphological evolution and the stresses and strains that develop as you cycle these materials. And so, yeah, the properties of the SEI, the chemistry, the even mechanical properties of it are really critical for operation. And I think that you're right in saying that it's not something that we think about, and we tend not to think of it even as a component. When I listed the basic components, I didn't mention that, but it's really critical for the performance, and it's something that develops sort of in situ in the cell. We generally don't dictate this is what the SCI will be before we build the cell. It has to be developed as during cell function. And so it's important but very complex aspect of cell performance and cell function.
And like you were saying, with these next generations, there's a lot of changes. And so quickly to go back, graphite, like you said, it's just a holder of the ions. It doesn't interact. It just goes in and out. And so now when you talk about these promising new materials that do react with the lithium, could you walk us through what the materials, what materials will be used and how each one of those differs with the lithium rather than just holding it in place and letting it go?
Yeah. I think the two biggest ones that the battery field as a whole are pursuing are silicon and then lithium itself. If we could take a step back as to the motivation for using these new materials, like I said, graphite is particularly well suited because it can cycle for a long time. It's very durable, has very long lifespan, but unfortunately it doesn't really hold very much lithium. If you look at charge per gram basis, the specific capacity of our material, graphite can only hold 340 milliamp hours per gram of graphite. And that really limits, for the people using their electric car or charging their cell phone, that really limits just how long you can drive it or how long you can operate your cell phone before you need to charge it back up. So people want to find new materials that will just hold more lithium. And as I said, the two that people are really exploring are silicon and then lithium metal itself. Silicon can hold almost 10 times as much on a per gram basis, 10 times as much lithium than graphite can. And it's even higher for lithium. It might sound a little bit cyclical or circular, but nothing holds more lithium than lithium. And so that's really the motivation for looking at these next generation materials. You want something that can store a lot of lithium. Silicon, however, doesn't have this nice structure that we've talked about that graphite does. It's got this diamond cubic structure. It's three-dimensionally bonded. And so for lithium to get into the structure, it actually goes through an alloying reaction. You're disrupting the lattice. You're forming alloys between lithium and silicon, and not only are you forming those alloys, but you're de-alloying and re-alloying hundreds, if not thousands, of times in a practical cell in an EV. And so that really changes the mechanism of how our cell is functioning, but also presents a whole nother set of problems that we have to solve. And so silicon, while it might hold a lot of lithium, maybe doesn't have the durability that graphite does, because every time you put lithium in and take lithium out, you're disrupting that crystal structure. you might be forming voids or pores and really disrupting differentiating itself from the material that you started with. And if we go back to the SEI, this solid electrolyte interface, every time you disrupt the lattice in silicon, you open more surface area, you form more SEI, you lose active lithium, you lose electrolyte, and your capacity goes down. And so while it has this one great thing about it, holds a lot of lithium, silicon also presents a lot of problems. And there's a lot of research going on throughout the entire field to figure out how to solve those problems. How do we keep the advantages of silicon while avoiding the disadvantages? And similarly, the same questions are being asked and some of the same problems are being experienced for lithium. The mechanism of lithiation is different, and really the physics are completely different, but they still have it still has its own problems. In a lithium metal cell, you're not being stored anywhere. You have to plate directly onto a current collector, or there's no host to hold on to that lithium. And so you're effectively just doing electrodeposition in a cell. And if you guys go back to sort of your first year material science and you think about the pictures that are always accompany electrodeposition, what do you guys imagine? What kind of structures do you see?
Usually just Arrhenius. They don't really have any order, but I'm not quite sure if you're looking for a more specific structure.
But the word I was looking for is dendrite.
Oh yes, dendritic.
Lithium and metals like that during electrodeposition love to form dendrites. And so rather than getting nice smooth plating, you get these little trees. That's what the word dendrite comes from, that stick up out of the substrate. And dendrites also are higher surface area, also form more SEI. They are also very fragile, so they tend to break off, and all that lithium is no longer connected to the circuit and no longer participating in cycling. And so while lithium might seem like the ultimate goal, because it has such great specific capacity, like I said, it comes with this set of challenges, which are all solvable, hopefully, by material science, but comes with its own unique set of challenges. And that's really where the field is right now, specifically on the anode side. There's a whole other world on the cathode side, and even the separator side, the electrolyte side. Like I said, it's a complex ecosystem, but using the anode as examples, there are next generation materials that we're all sort of running after, but there's a lot of problems that we're all actively working on.
Got it. I guess I just wanted to ask, and this is purely because I did research with solid state electrolytes, but do you see generally, is there research being done for solid electrolytes kind of in the electric vehicle space? I know, at least when I was doing research, really that main constraint was just like not being able to match that performance of liquid electrolytes, but there is that safety benefit that comes with it. So I was just curious.
Oh yeah, sorry. I thought you meant from the manufacturing perspective, but you meant more from a cell perspective. Yeah, there absolutely is solid state research going on throughout, especially academia and national labs, but even in industry, there are startups that have come about focused on solid electrolytes. And as you mentioned, there are benefits that come along with that, but additional challenges in things like manufacturability and even still performance. And so it's definitely on people's horizons. But I think when you think about sort of immediate next generation materials and technologies, maybe solid state isn't quite there yet. But I think that's very much up for debate.
Yeah, I actually do solid state research right now in fabrication. And so to give more numbers to it, basically what you're saying is the conductivity is usually for liquid electrolytes somewhere between 10 to the -2 Siemens per centimeter squared, I believe, around there. And so the electrolytes that we're shooting for, like 10 to the -2 to 10 to the -3, so a magnitude order worse in some cases, is like a good goal. So from that point of view, that's conductivity. And then the real challenge is that most lab scale groups can only make these thick pellets about 1 centimeter to a ½ centimeter thick. And when you think about that, there's no good way to store that in a car. And so what we need to get to is a pouch cell. And so pouch cells are very flat. And so what that comes about is that you now need to make these pellets very thin. And these pellets are made out of powders that are very brittle. It's a ceramic. And so there's a lot of research, and something I'm doing is with creating flexible solid state films to be used in pouch cells. And so when you look about that, that's how you'll get there. But there's so many challenges with the conductivity, and like you said, with dendritic growth, dendrites can pierce through it, and if you have a brittle material, then it starts to crack. So there's lots of things to consider, but those are kind of the main ones that you need to overcome to even test the cell, and something that a lot of people are working on, but there's only 1 or 2 papers that have actually shown we can make a film. They don't even show any electrochemistry. So I think that, like Jeff said, is that it's going to be a while.
Yeah. And not only, so if you think about, you're talking about, well, we need to make a film at this lab scale.
Yeah.
And it's difficult even at the lab scale to get the electrochemical data and make those cells. You can sort of do the exercise of imagining how big a pouch cell is for a car, and think about the areas and aspect ratios that you need for those ceramic films to act as the solid state electrolyte. It's a very hard manufacturing problem. Without diverging too much, that's something that sometimes goes unspoken in the battery research, especially more the academic or national lab side. You not only need this to work, but you need it to work for 1 million cars. Oftentimes, like I said, that goes overlooked, but it's an aspect of the research that is really, really critical for actually getting these things to market.
Yeah. And just the last thing I'll add, and then we can move on, but a lot of the battery technologies, like Jeff said, is that they're oxides. So they're already stable in air. Graphite stable in air, NMC stable in air. But a lot of the most promising solid state electrolytes, such as LPSC, create hydrogen sulfide gas in air. And so now you have to think about how we're going to produce something that can be very hard to work with. And so it's just a lot of overcoming problems that liquid does not have. So very interesting problems to solve.
Yes.
Okay, so I wanted to take it like a step back to kind of like what this material science, the challenges that come with it, what that leads to in terms of just like consumers, right? And so Jeff, I just wanted to hear, what are kind of the main obstacles that keep people from buying EVs currently, and how can these be addressed with advancements in material science in the future?
Yeah, I think that's a really excellent question. And hopefully the answer can be illustrative of sort of the power of material science, because I have the opinion that essentially all the problems that people have with EVs, or the constraints that keep them from buying them, can be solved with really good material science. The 3 big things that keep people from buying electric cars are cost. They tend to be more expensive. Range anxiety. People are afraid that they won't be able to travel as far. And then fast charge, or the ability to charge your battery at a time scale akin to that of engine. And so, as I said, I think all of those can be solved, though, with material science. If you look, or if we can go back to, for instance, the conversation we had about silicon, it just holds more lithium. It can go further, or in a theoretical cell, it can go further for less material. And so the cost aspect then begins to alleviate. If you can use less material or a cheaper material to get the same or better performance, you can charge less for the cell and thus charge less for the car. If you can hold more lithium like you can with silicon or lithium, you can go further. You can, for the same amount of material, for instance, on a mass basis that you use of graphite, you're going to go further with silicon. And so I think those are 2 really sort of striking examples of just by one simple replacement, again, theoretically, you have lowered the cost and you've improved performance. And that is all boils down to a material swap out and overcoming the materials challenges that come with that material swap out. The third that I mentioned, the issue of fast charge, is also similarly a materials-based problem. When you think about what is happening inside of a cell during charging, you're pulling lithium in and out of a material, and how that material responds to that is the problem that we need to solve. And that one is a difficult one. There is a lot that goes into how quickly you can charge a cell without disrupting and damaging the active material and losing capacity. You want to be able to charge quickly but maintain performance. But something like silicon has been touted as a material that can charge quickly because of its mechanism of lithiation, that, when I say charge quickly, charge more quickly than graphite because of its mechanism of lithiation. And so all three of those, the range, the cost, and the fast charge, we've already impacted by swapping out one component of our cell. And like I said earlier in the conversation, when you look at this ecosystem within a battery, all of these aspects are still undergoing active research and we're still optimizing. No one part has been solved. You can bring down the cost of the cathode by getting rid of cobalt. It's a very expensive element. It has comes from areas of the world with some tenuous geopolitical situations. And so a great deal of research is going on the cathode side to use less cobalt in the cathode material or get rid of it altogether. And then suddenly your cost comes down. So like I said, all of those issues, cost, range, and fast charge, are in a very fundamental way related to the materials that we choose to go into our cell. And all of those are currently under investigation. All those aspects of the cell are currently under investigation to alleviate those issues that people have with EVs and alleviate those reasons that people don't want to buy them necessarily.
And something I've noticed, and I would love to hear your opinion on this, is that all those problems also, if we think about the battery industry, is not huge. And what I mean by that is the lithium ion battery itself is only like 40 years old. And unlike these other very mature technologies like steel manufacturing has been around for like hundreds of years. And so when we look at it now, all these companies are shifting, like all the big car companies in America are now putting more money into battery manufacturing. So new plants, more people. I think that the amount of change that we're about to see in the battery industry is going to be greatly increased with all this competition. But what do you think, Jeff?
Yeah, I think it's a good thing that all of these companies seem to be making that shift at the same time. Well, good and bad, because there is competition for resources in a very real way, whether that's the resources of what goes into a cell or the resources of who knows how to make them. So there is competition on that side. But in general, the fact that there's this movement to within the automotive industry, there's sort of this gross movement towards electrification is a good thing for everyone. Not just from an environmental perspective, but if everyone, it sort of normalizes the market and levels the playing field. If all of the companies are providing some EV options across different price points and across different performance types, it makes the industry better if we're all sort of moving in that direction.
So what do you think generally that timeline is where we see maybe that like full adoption of electric vehicles over petroleum-based vehicles?
That's a really difficult question to answer. And I wish I had a concrete answer for you. It also depends on sort of how you define full adoption. Because if you're talking about every new car being sold being an EV, that's a different answer from getting every ICE vehicle off the road, and those timelines vary by quite a bit. So I can't, like I said, I can't really provide a concrete answer for you, but I think you can look towards promises that different industry or different companies have made about how their lineups of electric vehicles will change over the coming years, the next 5 to 10 years. Many companies have said that they'll offer more EV options. GM has talked about expanding our electric vehicle lineup quite a bit in the coming years. But you can also look more at governments and state governments and how they are treating this transition from ICE to EV. I think it was New York who just released the statement that they're going to, by 2035, require that all new cars sold within the state need to either be electric or plug-in hybrid. And so it's moves like that that help accelerate that transition. I think California has adopted something similarly. And so as more states do things like that, as the industry as a whole makes that shift that we talked about in the last question, I think we'll see that turnover happen at a more rapid rate. But like I said, I wish I could say, by 2035, but I don't have that answer. But I think we should all be optimistic that that transition is accelerating because of moves both by industry and governments to make that push.
maybe looking more ahead in the future, I think one thing that's very important to note is that we've talked a lot about the lithium-ion battery, but there's a lot of different other types of batteries and a lot of different types for different uses. And so for EVs, it's basically consensus that lithium ions will be the primary mode of transfer. But in the future, 10 to 20 years in the future, could you maybe briefly talk about how different energy systems like iron air or LFP could potentially influence other parts of our lives, or if that's too broad, just what to be on the lookout in the next 10 years in terms of new terms of batteries in places other than cars?
Yeah, I think we're starting to get to the edge of my expertise, but I think you'll see that we start to employ energy storage in other places of need. One aspect is sort of grid scale storage or more mass energy storage for broader distribution. It's great to be able to power a car with electricity, but one of the key things, for instance, to switch over to renewables is the ability to store the energy from renewables in a efficient and safe manner. And I think that's one place where you'll see battery technology deployed, maybe even at a larger scale. When you talk about other technologies for energy storage, there are beyond lithium chemistries that people have looked at. I think that actually there are already companies who are commercializing sodium ion batteries. And so there are definite frontiers beyond lithium that we will continue to be explored, and frontiers beyond just batteries in EVs that will continue to be explored. And each of those chemistries and each of those applications and needs bring along a different set of challenges, a different set of advantages and disadvantages. So I think that the battery research field as a whole still has a lot on their plate and a lot of problems, good problems, interesting problems. There's definitely, like I said, still a lot on the horizon when it comes to energy storage materials in general.
Absolutely. So based on today's discussion, it seems like material scientists will continue to be in high demand in the battery industry, especially with the investments that various companies and organizations are making. So with all that being said, for our audience, what would you recommend they focus on, maybe in terms of courses or research or internships, so that they can pursue a career down the line in batteries?
Yeah, I think that's a really interesting question. From an undergraduate perspective, I would say less so in terms of coursework, more just in terms of what sort of research that you want to get involved in. One of the great things about universities, especially in recent history, is they really encourage undergrads to get involved in research. And it's very low stakes for the undergrad. You can sort of pop in and out of lab with very little activation energy. And so I would say if you have the opportunity as you're working through your undergraduate or master's to see what research is like in a battery lab and test it out for a few months or longer if you enjoy it. Like I said, it's difficult to answer that maybe from a coursework perspective because everyone has different interests. I, for instance, when I was an undergrad, studied both physics and material science because those were sort of the overlap of my interests, and becomes a bit of a self-fulfilling prophecy because those are the then research areas that I enjoy, and that overlap is sort of where I have tried to stay. But I know people who studied material science and mechanical engineering or chemistry, and all of those aspects still have applicability in the battery field. Like I mentioned, there's many types of materials that go into a cell. It spans a really broad spectrum, and you can imagine places where someone who did material science with a little bit of chemistry sprinkled on top, where they might thrive, or with some mechanical engineering where they might thrive. We didn't even talk about how all these cells are housed and protected when they go into a car, but there's a great deal of mechanical engineering that goes into that. Electrical engineering with how cells are diagnosed sort of in situ within the car, and how power is routed from different cells within the pack to make sure that everything is balanced. All of that involves electrical engineering. And so that's the great thing about material science, is so interdisciplinary. So I think what I would recommend to people is just find your niche of the things that get you excited and tailor your coursework to that. But almost more than anything, the research experience can really tell you whether or not you'll like something, because that's real boots on the ground. This is practical knowledge and experience of what goes into that research rather than just sort of the textbook knowledge.
Absolutely. Yeah, I've always said that kind of the hands-on experience really helps, not just, for your job search, but really for figuring out kind of what you want to do. And I think coursework is a great way to supplement that learning, but that hands-on experience is great as well.
Yeah, and you touched upon something of note there is while it gives you the knowledge base for sort of what you want to do, it also does create advantages for people if they do, after they leave undergrad, want to go into a battery company or want to study batteries in grad school. If they have experience in a battery lab, it gets a little bit of a leg up and makes you stick out. And so if that's something that is of interest to you, that's the type of experience that's going to make you stick out when it comes to the job hunt or the grad school hunt or what have you.
Absolutely. Well, thank you so much, Jeff, for joining us today. It was awesome kind of learning about just the different parts of lithium-ion batteries in the EV space. And I just really appreciated your insight into where we're at now and where we can be in the future.
Yeah, I'm happy to be here. And thank you guys for asking me to join you.
Of course.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSc Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.